Hi, today I would like to present SecoArc, a framework for architecting healthy software ecosystems. I'm pretty sure that you are all familiar with the Android operating system. This is a platform with open APIs provided by Google. External developers can develop mobile apps on the basis of this platform and publish them on Google Play and make them available for the users. Google makes also some partnerships with the other companies which are responsible to provide different kinds of hardware and software services. And this is an ecosystem of interacting human actors with software elements, which is referred as software ecosystem in literature. Software ecosystems are the result of a complex range of architectural design decisions at business and technical levels. For example, in Android ecosystem, users can get a free access to the platform and rate the apps. These design decisions can be defined very differently, which is the case in terms of existing ecosystems. The platform provider has the central role to create a healthy software ecosystem by taking the right design decisions. The health of ecosystem is referred as overall well-functioning of the ecosystem. Currently, due to the lack of knowledge, the platform providers do not know how to cope with the high architectural variabilities and what design decisions to make in order to address their business goals. The suboptimal architectural decision making lead in practice to business risks, technical debt, or the platform providers go out of budget because of the features that are rarely used in practice. In our work, we present SecoArc, which includes a modeling language and an architectural analysis technique. SecoArc enables platform providers to design ecosystem architecture and analyze the architecture and then compare alternative architectures with each other. We have implemented SecoArc in a tool. You can use this link to access the source code, or if you like, you can take a look at the tool demo. SecoArc has been used in a project namely on-the-fly computing proof of concept, or shortly POC. The general idea of on-the-fly computing is that individual IT services are composing machine learning techniques. The POC team would like to open the platform to external service providers. However, they face several variation points in the architecture, so they can imagine several architectures to be suitable. Using SecoArc, they have designed and analyzed alternative architectures. In the scope of this presentation, I am going to present one of these architectures, which is called semi-open controlled ecosystem. This is basically an ecosystem with open access to the platform and services. By the way, to prevent unleashed growth of the ecosystem, controlled software and marketing environment needs to be established. In this presentation, I am going to focus on one variability to show how SecoArc is used to address the variabilities in ecosystem architecture. We start with the SecoArc modeling language. The goal to introduce a language is that first of all, this language embeds the knowledge of more than 100 existing ecosystems. In our previous work, we have studied existing ecosystems and we have identified the architectural variabilities. By architectural variabilities, I mean the variable architectural design decisions. This knowledge is included in the meta model of the language. The language is basis for the architectural analysis, and it is designed for the managers who do not want to confront with too much detail. On the left side, you can see part of the meta model. Here it is shown that fee can be entrance fee, platform fee, or service fee, and fee is a business decision. On the bottom, you can see the concrete architecture, which is modeled using the SecoArc visual notations. Here, the third-party developers need to pay entrance fee to publish their services on the marketplace. On the right side, you can see the variability model. This is part of our previous work where we have identified the variabilities related to the business, application, and infrastructure design decisions. Two variation points are shown here. One is fee and billing. The knowledge of variabilities is reflected in the meta model, and there are also interdependencies between the variabilities. For example, if in an architecture any kind of fee is defined, then there must be also billing features in the architecture to enable online transactions. Such interdependencies and in general the semantics of variabilities are implemented using object constraint language, OCL constraints. Now we get to the architectural analysis technique, which based on the knowledge of 3 architectural patterns. Each pattern helps to achieve a high-level business goal and consists of a set of contextual factors. Contextual factors characterize organizational characteristics of platform providers. Each pattern consists of sets of architectural design decisions. Each set of design decisions support a quality attribute of ecosystem health. For example, sustainability, interoperability, and so on. The definition of these quality attributes can be found in the original paper. During the architectural analysis, the contextual factors defined by the platform providers and the design decisions are matched against each pattern. And the results of matching help to draw some conclusions regarding the architectural design decisions made in the architecture. Here I would like to briefly explain these 3 patterns. The first one is open source software-based ecosystem to create an ecosystem for development of open source software. Some typical design decisions are open entrance and open publish. The second pattern is resale software ecosystem to achieve business scalability. A typical example is mobile app ecosystems. Using rating and ranking features in such ecosystems is very typical. A mass number of third-party developers develop software on the basis of the platform. The third pattern is partner-based ecosystem. In this case, platform provider does not open the platform to everyone, but trusted partners are carefully selected. Software is very commercial and it can be safety critical. Typical design decisions are monetized documentation and monetized API. Here I would like to present the result of architectural analysis. The first part of the results is pattern suggestion based on the contextual factors given by the platform providers. Since the POC team defines the platform to be not safety critical and emphasizes on free use of software and third-party services, the analysis suggests to use OSS-based ecosystem as this pattern matches the best to the organizations that are low commercial or the platform is low critical. The second part of results is about pattern conformance. Here, the design decisions made in the architecture are matched against design decisions of the patterns, and the platform provider can see to which extent the architecture matches to each pattern. So in case of architecture 1, it matches the best to resale software ecosystem. The detail of this matching is also given to the platform provider and also some exemplary ecosystems. So the platform provider can refer to the real world ecosystems and orient him or herself during the process of decision making. The third part of results is about a quality attribute fulfillment. As I have mentioned, each set of design decisions support a quality attribute of ecosystem health. And here the result of matching is provided. Architecture 1 supports sustainability to a very good extent and also interoperability. So the detail of this matching is given in the paper. For example, rating and ranking is shown to improve sustainability, and using IDEs and shared libraries improve interoperability. Something that is not used in the POC ecosystem is bring your own license, a concept that allows third-party service provider to license their services using their own licenses. SecoArc also allows platform providers to model and analyze more than one architecture. In a comparative view, platform provider can see the difference between these two architectures in terms of quality attribute fulfillment or pattern conformance. In summary, currently there's a lack of systematic knowledge to create software ecosystems. In this paper, we have presented SecoArc. SecoArc helps platform providers to orient their design decisions with respect to existing ecosystems. It provides automatic support for design and analysis phases. It enables platform providers to perform comparison of ecosystem architectures. In the future, there's a need to perform more empirical work and identify more quality attributes and the relation to architectural design decisions. Currently, the ecosystem architecture defined by SecoArc is quite high level. In the future, we need to reduce this gap to generate code out of the models. I thank you for your attention.